All right, Gen Chem, we are going to learn about acids and bases today. Okay, so you've probably already heard of acids and bases a little bit, but we're going to get into the definitions of them. And today we're also going to learn some of the properties of acids and bases, and we are also going to learn how to name them. We've already learned how to name most of the bases that we're going to talk about, but we haven't done acids, so we're going to learn how to name them today as well. So let's get into this. Chapter 13, acids and bases. Okay? We're going to do the Arrhenius definition of acids and bases. And yes, there are more definitions of acids and bases, but they are beyond the scope of this class. If you have questions about them, please feel free to come and ask me about them, and I'll be happy to share them with you. Okay, so for an Arrhenius acid, acids produce hydrogen ions when dissolved in water. So for example, if I had some hydrochloric acid and I dissolved it in water, I would produce what we say is hydronium and the chloride ion. Notice the hydrogen from the hydrochloric acid joins the water to produce the hydronium. Now, we don't normally write the water in this equation. So what we would normally write in this equation would be this. We would just write hydrochloric acid ionizing to produce hydrogen ions in water and chloride ions in water. Now, this little AQ that I'm writing by these means aqueous, means dissolved in water. Aqueous, if I can spell it, O-U-S. It's just a fancy word for dissolved in water. Okay, that's all it really means. All right, so we produce these hydrogen ions in water that really, in all reality, do bond to a water molecule to produce hydronium ions, but they act as hydrogen ions. Okay? Now, when we talk about a base, bases, Svante Arrhenius bases produce hydroxide ions in water. And it looks like my Word document is freezing right now. Okay, so Svante Arrhenius bases produce hydroxide ions. Okay, so OH negative. So a good example of that would be if I dissolved sodium hydroxide solid in water. And remember, we're not going to really write the water. I would get a sodium ion and I would get a hydroxide ion. Now, this, once again, just means dissolved in water. Okay? So I would produce the hydroxide ions when I'm dissolved in water. So remember, Arrhenius acids produce hydrogen ions when they're dissolved in water, and Arrhenius bases produce hydroxide ions when they are dissolved in water. Okay, properties of acids, and you've probably seen this a lot. When you bite into a grapefruit or a lemon or a lime, what do you taste? They're sour. So acids are sour. Okay, so for example, lemons, limes, grapefruit. If you've ever had vinegar, straight vinegar, it is sour. Okay, so acids taste sour because the acid binds with the receptors in our tongue to produce that sour sensation. Okay, acids, when we use litmus paper, it turns blue litmus paper red. So anything that turns litmus paper red is an acid. Okay, if we use universal paper, so universal paper can go from dark red, hot pink, all the way to like a dark navy blue. Acids turn universal paper warm colors. And by warm colors, I mean yellows, oranges, and reds. If you've ever done color theory, warm colors are the reds, the oranges, and the yellows. So red, oranges, reds to oranges to yellows are what we will get for acids. Now, the reds and sometimes bright pink will also be here. These get stronger the more you go towards the reds and the bright pink. Yellows are our weaker acids, okay? And acids also react with many metals, okay? They will react with a lot of metals. Okay, let's talk about properties of bases. Okay, bases taste bitter. Okay, if you've ever had straight cocoa powder, it's pretty bitter because it's basic. If you've ever had straight, I'm trying to think of another food. Most of the food that we eat is actually acidic, honestly. But if you've ever had like alkali water, the pH alkali water, it tastes bitter because it is basic. Okay, so a good example of this is cocoa powder. That bitter taste is because it's basic. Now, bases turn red litmus paper blue. Ooh, and I can't spell today. Blue. Let's write that better. All right. And if we're using universal paper, and remember, universal paper is the paper that has all kinds of colors that we can go from reds, bright pinks, reds, all the way to navy, dark blues, indigos. It turns the universal paper the cool colors. And by cool colors, I mean green, greens to blues to, it doesn't really get purple, it goes more to indigos. Okay, and this gets stronger this way. So the darker the blue, the deeper the blue, the stronger the base is on universal paper. Okay, now when we touch bases, they feel slippery. Probably the most common base that you are familiar with is soap. When you wash your hands with soap, your hands get really slippery. So they feel slippery to the touch. Now, I want you to think about why your hands feel slippery when they're in soap. Just give it a minute. Think about why. Do you have an idea? Now, the reason that our hands feel slippery when we are touching a base is our cell membranes in our skin is basically made out of skin cells, right? Our cell membranes are made out of fat, right? Remember that bilipid layer from biology? Bases are really, really good at dissolving fat. They're also really, really good at dissolving protein. So the reason why our skin feels slippery when we touch bases is it's dissolving our skin, okay? It's able to dissolve fats and proteins. And I just spelled protein wrong. Come on, give me an eraser. Okay. It dissolves fat and proteins. So that slippery layer, it basically dissolves our skin. So that slippery layer is just our skin dissolving. Okay, so let's name acids really quick. There are two types of acids. There are acids that we call binary. Bi means two. So this is two-element acids. And they start with hydrogen, and then they have a nonmetal, where X is a nonmetal. Okay? So binary acids all begin with H, and they are bound to a nonmetal. And then we have ternary acids. They all also begin with H and are bound to a polyatomic ion. And I like to do HYO, where YO is a polyatomic ion. And we haven't talked about polyatomics for a while. And notice that the polyatomic ion has oxygen in it. So let me show you a list. Let's refresh our memory. These are our polyatomic ions that we were using before. They are in your notes when we go back to our naming, when we did our naming way back in November, if you remember. So we have our symbols, the names, acetate, ammonium, arsenate, benzate. Notice that we have carbons, hydrogens, arsenic, whatever. We have elements usually bound to oxygen. Not always, but the vast majority of these are bound to oxygen. So when we have these polyatomics, we have hydrogens bound to these, and they almost always have oxygen in them. Okay? So make sure that you have a handy list ready. You can flip back and forth in your workbook to the polyatomic list that's in your workbook. Okay, so let's learn how to name these. So binary acids all begin with the prefix hydro. And we end with a suffix ic, and then we add the word acid. So let's break this down a little bit. So if I have a binary acid, I would call this hydro. And then X, I'm going to use the root of X's name, and then I'm going to put on the suffix ic, and then I'm going to add the word acid. So hydro, the root of X's name from the periodic table, plus ic, and then the word acid. Okay? So let me give you some examples of that. So if I had, and yay, my computer is freezing again. Let's give it a minute. Hopefully it will be able to think and do the things that it needs to do. So if I have HCl, chlorine is my nonmetal. So the root of chlorine is chlor. So I would call this hydrochloric acid. Hydrochloric acid. Okay? If I had HI, this is iodine. So the root of iodine is IO. So this would be hydroiodic acid. And if I had this, H2S, S is sulfur. This one we don't just do sulfic, we actually do sulfuric. This one we actually use the whole name. So this would be hydrosulfuric acid. Okay, now I'm trying not to put a space in here, but I am putting a space in here. There shouldn't be a space. So this would really be hydrosulfuric acid. Okay, so the hydro and the root name all are one word, and then acid is a second word. Okay, so make sure that this is one word and this is a second word. Okay, so this is how we name binary acids. Okay, now remember, they only have two elements, hydrogen and a nonmetal. So let's go to our ternary acids. Ternary acids never begin with the prefix hydro. Never, ever, ever. Do not use hydro, okay? We are going to look at the names of the polyatomics. So if you look at the polyatomics, you'll notice that some of them end in ate. So let's look at some of them. So I have acetate, ate. I have arsenate, benzoate, bicarbonate. Some of them end in ite. So let's look at what the eights end up with. So 8, we're going to drop the 8. We're going to drop that 8 and we're going to change it to ic. So we name those ic acids. And the ones that end in ite, we're going to drop that ite and we're going to change it to us. So we call these us acids. And yes, we add the word acid at the end. Okay? So let's skip down to the bottom of this page, and I'm going to show you some names. Here we go. All right, so let's look at each NO3. So we need to look at what NO3 is. Okay, so let's look for NO3 on our polyatomic chart. And if we look at NO3, and it's a -1, so to match it, I have to put one hydrogen on there because the sum of the charges has to equal 0. So we want 0 charge. So we're going to have HNO3 here. This ends in 8. So we're going to change that 8 and we're going to put ic. So this is going to be nitric acid. So this will be nitric. Oh, and I spelled that wrong. Nitric acid. Okay, make sure your spelling is good. Okay, let's look at something that's similar, HNO2. NO2 is not nitrate, so what is it? Let's look here. So if I look for NO2, it's right below here. NO2 is nitrite. So ites turn to us. So this is going to be nitrous acid. So this is going to be nitrous acid. Okay, so notice the ic tells me that I'm coming from an 8, so I know that it's nitrate with some hydrogen. Us tells me it's coming from an ite, so I don't know that this is nitrite with some hydrogen. Okay, let's look at another one. H2CO3. So we need to look at what CO3 is. So let's look up CO3. So if I look up CO3, let's see, CO3, it's carbonate. Notice it has a charge of -2. So if I have hydrogens that are +1 and carbonate that is a -2, to balance out those charges, I'm going to need 2 hydrogens. That's why the formula was H2CO3, because I've got to balance out those charges. Okay, so this is an 8. So we're going to change this to ic. So this is going to be carbonic acid. So carbonic acid. So this is going to be carbonic acid. And if you've ever drinking soda pop, you've had a lot of carbonic acid. This is how they generate a lot of that carbon dioxide that is in the soda pop. And it also gives that soda pop some sourness, that sour, sweet taste that we have with the sugar that they put in soda pop. Let's look at this one. So HClO2. So let's look at ClO2. So ClO2. Here we go. ClO2 -1, chlorite. It is an ite, so it's going to go to us. So this is chlorous acid. So we would say HClO2 chlorous acid. Okay, let's look at HClO3, just different by one oxygen. So let's look and see what ClO3 is. Okay, ClO3 is chlorate. So 8s turn into X. So this is going to be, did you guess it? Chloric acid. How'd you do on that guess? Okay, let's do HClO4. Or not 3, 4. Okay, so we're going to look for ClO4. So if I look for ClO4, it's not here. So let's go down. Here it is. Do you see it right here? It's perchlorate. So we're going to, 8s go to ic. So this is going to be perchloric acid. Okay, so perchloric acid. And let's do another one. Let's do HMNO4. So we need to look at MNO4. Okay? So if we look up MNO4 on this chart, MNO4 is permanganate. So this is going to be 8s go to ic. So this is going to be permanganic acid. So this will be permanganic acid. Okay, let's do some bases just to give you an idea of bases as well. Okay, so bases are hydroxides. So remember, when we named ionic compounds, we used the name of the metal, and then we used the name of the polyatomic. Okay? Now remember, group 1 and group 2 metals do not need Roman numerals. So sodium is a group 1, or in the first column of the periodic table. So we would just call this sodium hydroxide. Okay? And so anything in that first column, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, you're just going to call it sodium hydroxide, rubidium hydroxide. You don't need a Roman numeral. Now remember also that the group 1 elements have a charge of +1 and hydroxide has a charge of -1. So we are still balancing charges. Okay, so what happens if we have something from the second group? Remember, the second group of metals have a charge of positive 2. Hydroxide has a charge of negative 1. Excuse me. So for example, if I had strontium is of positive 2 because it's in that second column on the periodic table. Okay, if my computer will let me write, it would be awesome. So strontium has a positive 2, and remember hydroxide is a negative 1 charge. So to balance out a positive 2 and a negative 1, that means I'm going to need 2 of these to balance out that positive 2. So remember, whenever I have to multiply a group, like hydroxide is a group of elements, I have to use parentheses. So it would be written like this, and this would be strontium hydroxide. Okay, let's do another one really quick. What if I had iron that was a positive 3 and a hydroxide? How would I balance those charges? I would need 1 iron and I would need 3 hydroxides. So I would be Fe parentheses OH3. Now remember, the metals in the middle of the periodic table were transition metals, and they needed Roman numerals, and iron is one of them. So remember, the Roman numerals told us the charge. The charge of the iron is positive 3, so I would call this iron, if I can write, iron 3 hydroxide. Okay, and usually the 3 goes into the parentheses, and we use Roman numerals to do that. So there's a little refresher. Okay, now I just want to talk a little bit about acids and how they affect our environment. So let's go up to this really quickly. Okay, so note, some gases dissolve in water to form acidic solutions. Now, a lot of times when they dissolve in water, they are dissolving in water that is either gas or liquid in our atmosphere. All those clouds up in the sky, they will take these gases and dissolve them in the cloud. Like the gases that we produce carbon dioxide by burning fossil fuels, and we produce sulfur dioxide and sulfur trioxide by burning coal for our electricity, and our cars do a lot of nitrogen dioxide by burning the gasoline that we use. And they're in our atmosphere, and they're commonly found in our air in relatively small concentrations. It gets a lot worse when we have an inversion. Okay, these dissolve in water in our atmosphere, and they form acidic solutions. Okay, this is commonly known as acid rain. Okay, all rain is slightly acidic now because of these gases. Okay, so here's some of the reactions. Sulfur dioxide will react with the water and produce sulfurous acid. Sulfur trioxide will react with the water in the atmosphere and form sulfuric acid. And nitrogen dioxide will react with the water and form nitric acid and nitrous acid. Okay? When acid rain hits the earth, it is quickly neutralized sometimes by chemicals commonly found in the Earth's crust, like limestone. A great example of this is limestone or marble. Many statues in the world are made from limestone and or marble, and a lot of our buildings are as well. So let's take a look at what happens when this hits the limestone or the marble statue. So here's the formula for limestone. It's calcium carbonate, and if I have sulfuric acid, reacting with that as the rain falls, I will make calcium sulfate and water and carbon dioxide gas. So I get a lot of reactions off of this. Now, here's an example of a statue that has been kind of worse for the wear because of the acidic rain. And this statue is found in Washington, D.C. So notice this picture in 1944 of George Washington. He's pretty intact, and we can see the facial features. We can see the detail of his cravat around his neck and his collar. And now look at it about 60, 70 years later. The detail of the feather on his cap is mostly gone. His face is pitted. His nose has fallen off because his cravat is mostly gone. And look at all the pockmarking on the marble behind him as well. So over time, these statues and our buildings that are made out of limestone can show the effects of being exposed to this acid rainwater. Okay, so that is one of the detrimental effects of acid rain. It is not the only detrimental effect either. It affects wildlife and it affects birds, plants, animals, especially fish. So if you want to know more about that, I'm also happy to answer those questions. All right, have a great day and we'll see you later. Bye.